What's up guys, this is Massey. Welcome to another video. This video I want to have a review of magnetism questions. First one, determine the magnitude of the maximum magnetic force that could be exerted on a proton of mass 1.67 times 10 to the power of negative 27 kilograms moving through a magnetic field of magnitude 1.5 Tesla at a speed of 6 times 10 to the power of 6 meters per second. What is the magnitude of the maximum acceleration of this proton? So first of all, I need to find out the maximum magnetic force. Let's see what is given. Mass is given 1.67 times 10 to the power of negative 27 kilograms. We are talking about proton, so the charge of proton, we know it's 1.6 times 10 to the power of negative 19 coulomb. Magnetic field strength, we show it with B, 1.5 Tesla, and the speed is 6 times 10 to the power of 6 meter per second. What's the relationship between magnetic force and all this information? We can say F equals to B V Q sine theta. F is the magnetic force, B is magnetic field strength in terms of Tesla, V is velocity in terms of meter per second, Q is charge, sine theta. Theta is the angle between B and V, between magnetic field direction and velocity of the charged particle. So F equal, when we are talking about maximum, it means that sine theta must be maximum. And sine theta is maximum, which is 1, when theta is 90 degrees or when they are perpendicular. When B and V are perpendicular, it means that theta is 90. So F equals to B, V, Q. B is 1.5. V is 6 times 10 to the power of 6. Q is 1.6 times 10 to the power of negative 19. That's going to be 1.44 times 10 to the power of negative 12 Newton. That's the magnetic force. In the second part of this question, it says, what is the magnitude of the maximum acceleration on this proton? So we're going to use second Newton's law, F equals to ma. It means that A equals to F divided by m. F is the force, we already calculated, 1.44 times 10 to the power of negative 12 divided by mass, which is 1.67 times 10 to the power of negative 27. So we have 1.44 times 10 to the power of negative 12 divided by 1.67 times 10 to the power of negative 27. That's going to be 8.62 times 10 to the power of 14 meter per second squared. This is the acceleration. Next question. A shock absorber used in building a structure to withstand earthquakes uses the properties of tiny iron particles suspended in oil. In the presence of a magnetic field, the particles align and make the liquid nearly solid. The liquid is activated by a magnetic field with a magnitude of 0.08 Tesla. A particle with a charge of 2 times 10 to the power of negative 11 coulomb moves perpendicular to the magnetic field with the speed of 4.8 centimeter per second. Determine the magnitude of the force that the particle will experience. So let's find out what kind of information we have. First of all, we need to see this one is 0.08. That is the magnetic field strength, 0.08 Tesla. Then the charge is given, which is 2 times 10 to the power of negative 11 coulomb. It says moves perpendicular to the magnetic field. It means that V and B forms 90 degrees. So theta is 90 degrees and velocity is 4.8 centimeter per second. It says determine the magnitude of the force. Like previous example, F equals to BVQ sine theta. B is 0.08, V is 4.8, and it is centimeter per second. We need to convert it to meters per second, so I need to divide it by 100. Q is 2 times 10 to the power of negative 11, and sine 90 is 1. That's going to be 0.08 times 4.8 times 2 times 10 to the power of negative 11 divided by 100. That's going to give me 7.68 times 10 to the power of negative 14 Newton. That's the magnetic force. Next example. Figure below shows a straight conductor between the poles of the permanent magnet. If a current is moving in the direction indicated, what is the direction of the force on the conductor due to magnetic field? So in this kind of cases, you need to use right hand rule. In right hand rule, thumb is showing the I or electric current direction. Four fingers showing the magnetic field direction, and then palm of your right hand is going to show you the direction of the magnetic force. So in this case, thumb is going up, four fingers is going left, so it means that magnetic force is gonna come out of the page. So we show it like that. That means come out of the page. If it's going into the page, we show it like that, into the page. But the answer to this question is come out of the page. Now in this example, figure below shows the magnetic field around the current carrying wire. The arrows indicate the direction of the magnetic field. Part A, in which direction is the current? So if we have the thumb on the wire and the rotation of four fingers is showing the magnetic field, then we can find out the direction of electric current. So if our thumb is going towards right, then the rotation of four fingers of your right hand is going to show you the rotation of B in here. So that's the A. B, it says in which direction should the current move to reverse the magnetic field direction. So it's going to be the other way around. So that's the answer to part A. B, that's the answer to part A. Now in next example, it says in figure below a wire is shown to carry a conventional current in three different directions. Determine the direction of the magnetic field that will produce a magnetic force in each case. So again, thumb is showing I direction, four fingers showing B direction, which we need to find, and then palm of your right hand is going to show you the F direction. If we show the thumb toward right and palm toward up, then four fingers is going to be into the page. So that's the direction of the magnetic field. It's going to be into the page. Next one, thumb is gonna come out because that's the direction of I, and your palm is showing the F direction, which is gonna be toward north. If you do it such a thing, your four fingers is gonna be toward right. So that's the direction of the magnetic field. And the last one, you have thumb is going into the page and palm is gonna be to the left. So in this case, B is gonna be toward down or toward south. So that's how we find out the magnetic field direction using our 4 fingers of the right hand. The magnetic field in figure below has the magnitude of 3 Tesla. Determine the magnetic force experienced by part A, an electron at rest, an electron moving upward at 2 meters per second, and part C, an electron moving to the left at 2 meters per second. So we know F equals to B times V times Q times sine theta. F is the magnetic force in terms of Newton, B is magnetic field strength in terms of Tesla, V is velocity, m over second, Q is the charged particle, and sine theta, theta is the direction between V and B. So A, it says electron at rest, it means that V is 0, so it means that F is 0 as well. So when electron or any charged particle is at rest, it means that there is no magnetic force. B, electron moves upward 2 meters per second. So it means that F equals to 3 times 2 times the charge of electron is 1.6 times 10 to the power of negative 19 sine 90, which is gonna be 9.6 times 10 to the power of negative 19 Newton. C, an electron moving to the left, it means that it's going this direction to the left at 2 meters per second. Part C, as you see here, they are parallel, so theta is 0, it means that sine theta is 0, sine 0 is 0, it means that there is no magnetic force, so magnetic force is gonna be 0. In next example, it says in figure below, an electron is traveling to the left, moves into a magnetic field directed out of the page, as you see here. Describe the path of particle through the field. So we need to use the right hand rule again. Thumb showing velocity direction, 4 fingers showing B, and palm is showing the force direction. So thumb is going left, 4 fingers up, so force is gonna go in north, but this is applicable only for positive charges. Right now we are dealing with electron, which is negative. So what we need to do, we need to just make it opposite. So instead of going up, it is gonna go down. Force is gonna be downward. One more time. Velocity is going left, so thumb going left. 4 fingers is up. Palm of your right hand is showing up. This is for positive charge, but here we are dealing with negative charge. So instead of going up, it is gonna go down. So force is gonna go down, and the path is gonna be something like that, because we have force in south direction. Next one, a magnetic field has a strength 0.3 Tesla. A particle with a positive charge of 0.006 coulomb and speed 400 meters per second is moving perpendicular to the magnetic field. Determine the magnitude of the magnetic force exerted on the particle. So we can say F equals to B V Q sine theta. B is given, which is 0.3. V is given, which is 400. Q is 0.006. Sine 90, because that's perpendicular, it's going to be 1. So it's going to be 0.3 times 400 times 0.006. That's going to be 0.72 Newton. That's the magnetic force. Next example. A proton moves into a magnetic field B equals to 5.4 times 10 to the power of negative 2 Tesla in the direction perpendicular to the field at speed of 4.8 times 10 to the power of 5 meter per second. Determine the force. Again, BVQ sine theta. B is 5.4 times 10 to the power of negative 2. V is 4.8 times 10 to the power of 5. Q is 1.6 times 10 to the power of negative 19. Sine 90, which is 1. 5.4 times 10 to the power of negative 2 times 4.8 times 10 to the power of 5 times 1.6 times 10 to the power of negative 90. That's going to be 4.15 times 10 to the power of negative 15 Newton. That's the magnetic field. An electron moves with the speed of 6.9 times 10 to the power of 3 meters per second. So velocity is 6.9 times 10 to the power of 3 meter per second in a direction perpendicular to the magnetic field, directed south to north, and of strength 1.3 times 10 to the power of negative 2 Tesla. What are the magnitude and direction of the force on this electron? If the electron is moving east to west, that's velocity. This is the direction of B. So if we have thumb going toward left, 4 fingers toward north, then palm of your right hand showing the into the page. So this is the direction of magnetic force. How to find out the magnitude is going to be BVQ sine theta. B is 1.3 times 10 to the power of negative 2. V is velocity, 6.9 times 10 to the power of 3. Q is the charge of electron, 1.6 times 10 to the power of negative 19. Sine theta is sine 90, which is going to be 1. So that's going to be 1.3 times 10 to the power of negative 2 times 6.9 times 10 to the power of 3 times 1.6 times 10 to the power of negative 19. That will give me 1.435 times 10 to the power of negative 17 Newton. That's the magnitude of the magnetic force. A small particle with a charge of 5 times 10 to the power of negative 16 coulomb. So Q is 5 times 10 to the power of negative 16 coulomb. Enters a magnetic field strength of 2.4 times 10 to the power of negative 2 Tesla at right angles. So theta is 90 degrees. With a speed of 4.9 times 10 to the power of 5 meter per second, determine the magnitude of the magnetic force. F. So F will be BVQ sine theta. So that's going to be 2.4 times 10 to the power of negative 2. V is 4.9 times 10 to the power of 5. Q is 5 times 10 to the power of negative 16 times sine 90, which is going to be 1. 2.4 times 10 to the power of negative 2 times 4.9 times 10 to the power of 5 times 5 times 10 to the power of negative 16. That will be 1.51 times 10 to the power of negative. That's actually 4.8 times 10 to the power of negative 12 Newton. That's the magnetic force. 4.8 times 10 to the power of negative 12. An electron moves at of 3 times 10 to the power of 3 meter per second. So 3 times 10 to the power of 3 meter per second, perpendicularly into a magnetic field intensity of 2.4 times 10 to the power of negative 2 Tesla. Determine the force on this particle. We are dealing with electron. Electron Q is 1.6 times 10 to the power of negative 19 Coulomb. And it's perpendicular, so theta is 90. F will be BVQ, which is going to be 2.4 times 10 to the power of negative 2 times velocity, 3 times 10 to the power of 3, 1.6 times 10 to the power of negative 19. That is going to give me 1.152 times 10 to the power of negative 17 Newton. That's the magnitude of the magnetic field. An electron traveling at right angles to a magnetic field with a speed of 8 times 10 to the power of 4 meter per second experiences a force of 3.8 times 10 to the power of negative 18 Newton. Determine the magnetic field strength. So now we need to find B. They are perpendicular because it says right angle. So theta is 90. Electron is Q is negative 1.6 times 10 to the power of negative 19 Coulomb. So F equals to BVQ sine 90, which is going to be BVQ. F is given, V is given, Q is given. We need to find B. So B equals to F divided by VQ. F is 3.8 times 10 to the power of negative 18 divided by V, which is 8 times 10 to the power of 4. Q is 1.6 times 10 to the power of negative 19. That's going to be 2.97 times 10 to the power of negative 4 Tesla. 2.97 times 10 to the power of negative 4 Tesla is the magnetic field strength. Next example. An oxygen ion with a mass of 2.7 times 10 to the power of negative 27 kilograms. So M is 2.7 times 10 to the power of negative 26 kilograms, is moving with the speed of 310 meter per second in direction perpendicular to the magnetic field of magnitude B is not given because it says what is B. The acceleration is 1.5 times 10 to the power of 9 meter per second square. So it means that we have only one force, magnetic force, which is BVQ sine theta. Theta is 90, so that's going to be 1 BVQ. On the other hand, F equals to MA. So B will be equal to MA divided by VQ. M is 2.7 times 10 to the power of negative 26 times A, which is 1.5 times 10 to the power of 9. V is velocity, which is 310 meter per second. Q is charge of oxygen ion, which is 2 electrons. It's going to be 2 times 1.6 times 10 to the power of negative 19. So that's going to be 2.7 times 1.5 times 10 to the power of negative 26 times 10 to the power of 9. That's going to be 4.05 times 10 to the power of negative 17 divided by 310 times 2 times 1.6 times 10 to the power of negative 19. It's going to be 9.92 times 10 to the power of negative 17. That's going to be 0.41 Tesla. That's going to be the magnetic field strength in terms of Tesla. A nitrogen ion is traveling through an atmosphere at a speed of 520 meters per second. What is the approximate force on this ion on Earth's magnetic field when the ion is moving perpendicular, so theta is 90, perpendicular to Earth's magnetic field? Assume a value of 5.5 times 10 to the power of negative 5 Tesla for Earth's magnetic field. So B is 5.5 times 10 to the power of negative 5 Tesla. So Q is 1 proton, so F is BVQ sine 90, which is going to be 1. So B is 5.5 times 10 to the power of negative 5. Velocity is 520. Q is 1.6 times 10 to the power of negative 19. That's going to give me 4.57 times 10 to the power of negative 21 Newton. That's the magnetic force. Next example. It says a proton travels with the speed of 1.00 times 10 to the power of 5 meter per second east. The proton enters a research building that is using a strong magnetic field of 55 Tesla. When the proton moves eastward, the magnetic force acting on it is directed straight upward. It means that the velocity is this way. Magnetic force is going in north. And when it moves northward, when V is northward, there is no magnetic force acts on it. It makes sense. So it says determine the direction of the magnetic field. If we use the right hand rule, thumb is going velocity, 4 fingers must show the magnetic field direction, but we don't have it. But palm is going to show you the force. So we rotate the right hand to have palm toward up. So it means that magnetic field direction is going to be into the page. And since this proton is positive, 1.6 times 10 to the power of negative 19 coulomb. What is the magnitude of the magnetic force when the proton moves eastward? So BVQ sine theta, which is sine 91. So B is 55. V is 1.00 times 10 to the power of 5. Q is 1.6 times 10 to the power of negative 19. That's going to be 8.8 times 10 to the power of negative 13 Newton. That's the magnetic force. Next example. Assume an electron is moving at the speed of 2.5 times 10 to the power of 5 meters per second due west in a magnetic field 55 Tesla directed north to south. What is the magnitude of the magnetic force on it? So F will be BVQ sine theta, which will be 55, 2.5 times 10 to the power of 5. Q is 1.6 times 10 to the power of negative 19. Sine 90, which is 1. 55 times 2.5 times 10 to the power of 5 times 1.6 times 10 to the power of negative 19 times 1. It's going to give me 2.2 times 10 to the power of negative 12 Newton. That's the magnetic force. Now what is the direction of the magnetic force? The direction, again, we use the right hand rule. Thumb is going left, 4 fingers going down for magnetic field, and palm of the right hand is gonna come out of the page. So the force is going to come out of the page. So that's the direction of magnetic force. A particle is traveling with the speed of 400 meters per second parallel to the magnetic field, strength of 0.3 Tesla. The particle has a positive charge of 0.006 Coulomb. Determine the magnitude of the magnetic force exerted on the particle. So we know F equals to BVQ sine theta. Here it says parallel. The particle is traveling with the speed of 400 parallel to the magnetic field. So it is going, V is the same direction as B. So it means that the theta, which is the angle between these two, is 0. So sine theta or sine 0 is 0. So there is no magnetic force. So Fm is 0. Next example. How should a current carrying conductor be placed relative to the magnetic field to maximum the force on the conductor? It means that there must be perpendicular, theta 90, between the current direction and magnetic field direction. If a current carrying conductor is placed along the x-axis in the magnetic field and in the magnetic field along z-axis, what will be the direction of the magnetic force? Is x-axis, y, and z. Current going in x-axis. Magnetic field is going toward z-axis. So we need to use right hand rule. Thumb is going toward I, four fingers toward up. So it means that palm is showing this way. So force is gonna be on negative y axis. Toward negative side of y-axis is going to be the magnetic force direction. Next example. If a current carrying conductor is placed parallel to the direction of the magnetic field, what is the magnitude of the force acting in the conductor? So F equals to B times I times L times sine theta. Theta is the angle between B and electric current. So since they are parallel, it means that theta is 0. So sine 0 is 0, so F will be 0. So there is no magnetic force for this example. This example, a wire carries a conventional current along the z-axis, z direction, and experiences a force along the negative y direction. If the magnetic field is perpendicular to the wire, what is the direction of the magnetic field? That's x, z, y. So this is going wire. Negative y is gonna be the force. We need to find out the direction of the magnetic field. So thumb is showing the I. Palm of the right hand is showing the F direction. So four fingers is showing negative X direction because it's gonna go into the page. Into the page, it means that the opposite side of the X direction. So it's gonna be negative X direction, and that makes sense because it must be perpendicular to I and F. A straight wire of length 0.65 meters carries a current of 1.7 amp. The strength of the magnetic field in the region is 1.6 Tesla. If the force on wire is 1.1 Newton, determine the angle between the field and wire. The formula that relates all these parameters is F magnetic field force equals to B, which is magnetic field strength, times I electric current in terms of ampere, L is length of wire in terms of meter, times sine theta. Theta is the angle between I and B. So F is given, which is 1.1, B is given, which is 1.6, I is given 1.7, L is given 0.65 equals to times sine theta. So sine theta equals to 1.1 divided by 1.6, 1.7, 0.65. That's going to be 0.622. So theta will be inverse of 0.622. That's going to be 38 degrees. That's the angle between B and I. So sine theta is 0.622. Theta will be sine inverse of 0.622, which is going to give us theta equals to 38 degrees. This example, it says in figure below, a negative charge is moving in the downward direction near an electric current passing through a straight conductor. Determine the direction of the magnetic force on the charge. So first of all, we need to use right hand rule for this I. When we place the thumb for the I, it means that it generates the magnetic field around it, which is moving this way. So it is going into the page this side, and it comes out of the page this side. On this particle, we need to use the right hand rule again. Thumb is going down, B is going to be 4 fingers, and F is showing outward. But since it's negative charge, is going to be the opposite around. Remember, the right hand rule is for positive charge. If it's negative, you need to make it the other way around. So since it's going out, for negative is gonna go in. So it means that force is gonna go inward in this case. That's the direction of the magnetic force. Next example, a 10 centimeter long segment of a straight wire is perpendicular, so theta is 90, to a magnetic field, which is 1 Tesla. If the wire experiences a force of 2.5 Newton, determine the current through the wire. So again, F equals to BIL sine theta. Sine 90 is 1, so this part is going to be 1. F is 2.5. B is 1. I is not given. L is 10 centimeter, but we need to convert it to meters. So 10 divided by 100 is going to be 0.1. So I times 0.1 equals to 2.5, which is 2.5 divided by 0.1. We don't need to use the calculator. 2.5 divided by 0.1 is going to be 25 ampere. So that's how we find out the electric current in the wire. 25 amp. Next example, if the charge of the particle moving in a magnetic field is changed from positive to negative, what happens to the direction of the magnetic force on this charge? It's gonna make it opposite. For example, if the force is going right, then it becomes left. If it's into the page, it becomes out of the page. If it was going up before, it is gonna go south now. So that's how it changes when the charge of the particle changes from positive to negative or from negative to positive. Next example, a conductor 25 centimeter, so length is 25 centimeter divided by 100 is going to be 0.25 meter, carries a current of 50 ampere. It is placed in a magnetic field of strength 49 Tesla. Determine the force exerted on the conductor when it makes each of the following angles: 0, 45, and 90. So F equals to BIL sine theta. The first one, we don't really need to calculate it because sine 0 is going to be 0, so f is 0. B is going to be f equals to BIL, which is 49 times I 50 times L 0.25 times sine 45. So that's going to be 49 times 50 times 0.25 times sine 45. That's going to be 433 Newton. Now part C, everything's same except the angle. Sine 90, sine 90 is 1. So 49 times 50 times 0.25, that will be 612.5 Newton. That's the magnitude of the magnetic force. Now in this example, a 5 centimeter segment of wire, so L is 5 centimeter, we need to convert it to meter. 5 divided by 100 is going to be 0.05 meter. Carrying I, which is 2.5 ampere, inside the solenoid is perpendicular to this 125 Tesla. Determine the magnitude of the magnetic force. So it's perpendicular, so F equals to BIL 25 times 2.5 times 0.05. 25 times 2.5 times 0.05. That's going to be 3.125 Newton. That's the magnetic force for this example. A 36 meter length of electric wire carries a current of 22 amp. So L, length is 36 meter. Electric current is 22 amp. From a transformer to a building in a west to east direction. The magnetic field of Earth at transformer location is horizontal and directed from south to north. South to north is B. And wire is west to east. And B is 5 times 10 to the power of negative 5 Tesla. Determine the magnitude and direction of the force. They are perpendicular, so F equals to BIL 5 times 10 to the power of negative 5. I is 22. L is 36. So we have 5 times 10 to the power of negative 5 times 22 times 36. That's going to give me 0.0396, or I can say approximately 0.04 Newton. How to find out the direction of the magnetic force? We need to use the right hand rule. Thumb is going right, 4 fingers going up. So palm of the right hand is coming out of the page. So that's the direction of the magnetic force. Next example. A 30 centimeter length of appliance cord carries a current of 4 amp. So first of all, length is 30 centimeter. Right away we need to convert it to meter. 30 divided by 100 is going to be 0.3 meter. I is 4 amp. Oriented right angles, magnetic field is 0.3 Tesla. Determine the magnitude of the magnetic force. F equals to BIL. B is 0.3. I is 4. L is 0.3. We don't really need to use calculator. 0.3 times 4, 3 times 4 is 12. So 0.3 times 4 is going to be 1.2. So this part is 1.2. On the other hand, 12 times 3 is going to be 36. But here we have 1.2 and 0.3. So it's going to be 0.36 Newton. That's how we calculate it without using the calculator. And final question, it says straight conductor is carrying a current of 5 amp moving toward east, a magnetic field of 0.2 Tesla points straight up across 1.5 meter conductor. What is the force acting on the conductor? So since they are perpendicular, F equals to BIL, sine 90 is 1, so I don't need to write it, 0.2 times 5 times 1.5. Here again, we don't need to use calculator. 2 times 5 is 10, so 0.2 times 5 is 1. 1 times 1.5 is going to be 1.5 Newton. That's how we calculate it. So that's the magnetic force in terms of Newton. I hope you enjoyed this video. I solved, I think, around 40 different questions regarding magnetism. Please leave me a comment if you have any question, and you can follow other playlists regarding physics, math, and chemistry. Thank you for watching and have a great day.